Let us start this lecture with a thought process from famous Swami Vivekananda. He says that you fail only when you do not strive sufficiently to manifest infinite power. It's a very great statement, and one must mull over it to get the power of the statement. And let us recall what we learned in the last lecture. By considering flow to be isentropic in a nozzle, or rather by considering the flow to be isentropic in a variable area duct, we found out a relationship between the area and Mach number, and we also looked at how this can be really function of Mach number. In other words, Mach number will be dependent on the area ratio, that is A at any cross section with respect to the choked area, and also it is a function of the gamma, and we looked at that for a particular area ratio one can have two solutions, one is for subsonic flow, other is for supersonic flow. And we have also argued that why the divergent portion is required to be added with a throat to the convergent portion in case of a convergent divergent nozzle or the Laval nozzle, to achieve the supersonic velocity at the exit of the nozzle. And today we will look at basically the flow processes in a convergent divergent nozzle or the Laval nozzle. Let us look at this convergent divergent nozzle, and you can see that it is having a convergent duct, and this is your divergent duct, and this is your throat area. And keep in mind that this is connected to a reservoir having certain pressure of PT2 and TT2, and velocity is basically almost 0 in this reservoir. And if the back pressure here, I can say this is PB, is same as the PT2, there won't be any flow. But if it is lower than that, there will be definitely flow will be occurring through this convergent divergent nozzle. When there is a back pressure is lower down, there will be certain velocity at the this inlet to that thing, and then the velocity of course increases when it is really acting as a nozzle. And we will see that what is happening when you are having certain pressure change of the back pressure, and we will see what is happening by considering the cases. What we are plotting over here is P by TT2, and keep in mind this is your inlet and this is your exit, and this is your, you can say it is a inlet, and we can consider the flow to be quasi one dimensional. This is the inlet, this is the exit, and the throat area will be, this is your throat cross section, the minimum area of this convergent divergent nozzle. And let us consider that for certain pressure of PV for which this nozzle is designed, particularly for the certain Mach supersonic Mach speed or a Mach number greater than 1, and if this PB is same as that for which it is designed, which is equal to the P, then the flow in this convergent nozzle will be isentropic, and then it will be basically pressure will be reducing, and then the flow will be subsonic in this region, and then here it will be Mach number is equal to 1 at the throat section. That means it has reached really choked mass flow condition, or it is aerodynamically choked, such that Mach number is equal to 1, and then it will be expanded further in the divergent duct, and you will get this isentropic relationship whatever for which it is designed. This is basically isentropic flow. But however, when this nozzle is started, the back pressure need not to be same as for which it is designed. So, if the back pressure is, let us say A, that means it is little lower than the reservoir pressure, then what will happen? There will be decrease in pressure here due to increase in velocity, because this will be convergent portion will be acting as a nozzle, because the flow is subsonic at the inlet. And however, this velocity will be also subsonic, the flow will be subsonic at the throat, and then this is the divergent portion. So, then the pressure will be increasing, because it will be acting as a diffuser. There will be deceleration of the flow, and so also increase in pressure. And at this moment it is not acting as a nozzle, because velocity is not reaching the values, right. Particularly the divergent portion will be acting as a diffuser. And let us say that the PV pressure or the back pressure lowers down a bit, let us say it is around pressure PV. In such a cases, we are considering the flow will be accelerating in the convergent portion of this nozzle, and at the throat it will reach a pressure, critical pressure, at which the sonic wave will be there on the throat. That means the Mach number is equal to 1, and however, the pressure, back pressure is much higher than the throat pressure. This is basically corresponding to the ratio, the is equal to 0.528 for gamma is equal to 1.4, and this is known as critical pressure. At this condition is basically P by PT2 is critical pressure for gamma, and these values will be different for different gamma. If I take gamma 1.2, it will be 0.564. So, depending on gamma, this value critical pressure may change, but here the pressure, back pressure being much higher than the pressure which will be happening at the throat. Therefore, it is being decelerated in the divergent duct, and the flow will be subsonic in nature even in the divergent duct. And although the throat has reached the Mach number equal to 1, but if the pressure is lowered down further, such that it will reach the PV as a C here, and such that the keep in mind this PC, the back pressure at the corresponding to this point C is lower than the throat pressure. So, therefore, the flow is accelerated till the throat, and it is accelerated further in the divergent portion, and such that it has the pressure is goes with isentropically and reaches a much lower pressure than that of the back pressure or the exit pressure at the in this nozzle. As a result, what will happen? This pressure is lower, and it has to undergo a shock to be formed in the nozzle itself. This is your shock, normal shock. And as you know, after downstream of this normal shock, the flow will be subsonic, and this divergent portion of the nozzle downstream of the shock will be acting as a diffuser, because the flow is subsonic and it is there is an increase in area, and such that there will be also increase in pressure. That means the location of this sock is decided by how much the total pressure increase across the sock plus the increase in pressure due to the deceleration of the fluid in the divergent portion. And if you lower this back pressure further, let us say to a point D, where the sock has now moved from the interior of this diverging portion to the exit of this nozzle almost. Of course, in between the sock can be moving toward the nozzle exit as the back pressure keeps on decreasing, right, and such that this normal sock is being formed here. But if you lower the back pressure further to the E, you may find that again there is a sock will be now becomes exiting out of the nozzle, and but it is attached to the nozzle wall at the exit point, and this sock will be formed, and this is basically the oblique sock. And keep in mind that for this condition from C to the D and EF, any other condition in between this pressure range, the nozzle is over expanded as compared to the back pressure. Therefore, this is known as over expansion. And if of course it reaches the same pressure for which if the back pressure reaches the same pressure for which this is designed, that is PE, then you will get the isentropic flow in this nozzle, of course except the boundary layer. There will be definitely boundary layer, and except that region other places it will be isentropic in nature. And generally for accelerating flow, the boundary layer thickness will be much lower and which will be closer to the wall of the nozzle. So, if the back pressure lowers down below the pressure E, then you will see that it will be reaching the exit pressure will be equal to the PE, and which is much higher than the back pressure. Therefore, there is a chance that there will be gas will be further expanded the downstream of this nozzle or beyond the exit, and there will be fan expansion fan which will be coming over here, and through which it will be there, and these are known as expansion fan. The flow will be taking place in this direction, so also the flow, and this is known as under expansion. And the losses in this nozzle during the over expansion and under expansion will be much higher as compared to the fully expanded, that is corresponding to the isentropic flow in a nozzle for which it is designed. And however, over expansion is much higher as compared to the pressure losses during the under expansion. So, you should keep in mind that it is the flow is quite complex, and when the rocket nozzle is being operated in real situation, the rocket engine has to move from the sea level to certain altitude. Let us say it is designed for certain altitude, and at that point it will be really fully expanded, but however below that altitude it will be over expansion, and above that it will be under expansion kind of thing. That means the back pressure, which is same as that of the atmospheric of altitude in which the vehicle is moving, keeps on changing along with the altitude. Therefore, all these processes of over expansion, under expansion, fully expansion will be taking place, one cannot avoid. However, one has to design in such a way that extent of over expansion has to be minimized, so that the losses will be minimized, and of course, there is a other kind of nozzles there which will be adaptable to the altitude or the back pressure with minimum losses. Let us now summarize what we have learnt in this flow features in a D level nozzle. So, what we learnt that for pressure Pa by Pt less than 1, the flow is subsonic at the throat and also the convergent portion of the nozzle, and also in the divergent portion of the nozzle, and this divergent portion acts as a diffuser. That means the flow will be decelerating in this divergent portion of the duct. And when the Pv by Pt is less than 1 and the flow is not only subsonic in the convergent portion, and it may happen that in the divergent portion flow will be also subsonic because the Pb, the back pressure is greater than the throat pressure at the critical condition. So, therefore, the flow is subsonic, and however, when the Pc by Pt is less than 1 and the Pc happens to be less than the throat pressure, so then throat will be not only attaining the Mach number 1 or the sonic condition, but the flow in the downstream of this throat will be supersonic, and a normal shock will be formed depending on the how far this back pressure is away from the expanded pressure or fully expanded pressure. And when Pe is by Pt2 is less than 1, that means it is basically the back pressure is same as that of the Pe, thus there will be shock free isentropic flow across the nozzle, because for this Pe the nozzle is designed. And when the P by P2 is between this design back pressure and it is greater than the Pb or Pc, then the normal shock and oblique shocks are formed, and we call it basically over expansion. And when the pressure back pressure is less than the Pe for which the nozzle is designed, there will be expansion wave are formed because it is the nozzle is under expanded. So, that we have seen, this is the regime what one has to, these are the regimes a convergent divergent nozzle experiences during the flight along with the altitude of that we have already discussed. So, let us now look at that what happens when it is interacting with the atmosphere. And if you look at, I have shown you a nozzle, this is a rocket nozzle, and convergent divergent nozzle, and it is basically the hot gases are emanated from the exit of this nozzle, and it undergoing the various shock patterns, and then you can see that the jet boundaries, you can see these are the, because here it is the atmosphere pressure which will be all the time it will be remaining constant, and this is the jet boundary, you can say, or the free boundary. And keep in mind that pressure is across this boundary will be remaining constant because the atmospheric pressure cannot be changed. So, hence the jet boundary P must be equal to the P infinity, that means P A is equal to P infinity, and that is the condition on which we will be looking at it. Keep in mind that we will have to see that how does this shock which will be emanated from the exit of this nozzle will be interacting with the free boundary. And let us consider a case what is happening. All of you might be knowing that the shock, whenever it will be impinging into the wall or the solid wall, then naturally it will be reflected back as a shock itself, and so also the expansion wave, when it is impinges into the solid wall, it will be reflecting by the expansion waves. But let us see that what happens with a free boundary, whether this same thing will be happening or not. Let us consider that a shock wave on an isobaric boundary, because the atmosphere pressure remains constant, therefore we call it will be remaining constant. Let us say that this shock is emanated from a nozzle, and then it is incident shock impinging into the boundary, and this is your free boundary and having the pressure P infinity. And as you know that when the flow passes through oblique shock or a normal shock, what will happen, there will be increase in pressure. That means the P2 will be greater than the P infinity. And if you look at the downstream, that in the whenever it will impinging that, then in this place the P3 will be really the less, P3 is less than the P2. Therefore, there will be an expansion wave which will be taking place, such that the P3 will be attaining the P infinity to keep this preserve that pressure to be same or isobaric in nature. So, and another thing you can also observe, there is a change in the boundary of that, the boundary turns upward, and as the fluid is moving this way, and therefore this is happening that whenever the shock is impinging into a jet boundary, then the expansion wave is reflected back. So, therefore, this is just opposite that what is happening on the wall. So, this is very interesting, you should keep in mind, because this is required to understand, to look at what are the shock structures happens when it is under expanded and over expanded, that we are going to discuss in the subsequently. So, let us look at this expansion wave on a isobaric boundary. In this case, let us say that this is basically a expansion waves which is emanating from the exit of a nozzle, expansion waves, and when it is impinging into this jet boundary, then what happens, like if you look at this pressure P2 will be lower than the P1, and however the P3 is will be basically greater than the P2. Therefore, there will be a compression waves which will be formed, because without that flow cannot really take place, compression waves, and these compression waves is coalesce into forming a shock. It all coalesce to form a shock. So, and such that the pressure P3 is same as that of the P infinity, that is the free boundary or the atmospheric pressure. So, therefore, this is just opposite things are happening, like expansion waves is when impinged into this jet boundary reflected as the compression wave and then converted into shock wave. So, to summarize that the waves incident on a free boundary reflects in the opposite manner, this you can call it as a unlike a reflection, and whereas for the when waves incident on a solid boundary reflects like manner, therefore, we can call is basically like reflection, and that is true for the shock and then expansion waves. And these features you should keep in mind, so that we will discuss. But another important point what I missed is that you can see this jet boundary is basically turned downwards towards the shock, unlike in the case of a incident shock, it is moving upward or away from this reflected expansion. So, therefore, this boundary, the free boundary will be changing depending on the kind of, whether it is a shock or a expansion waves is impinging into the boundaries. Therefore, you will find there is a increasing, decreasing, all those things, boundaries is changing. So, that will be very clear, and then it goes on changing these things till the shock strength is reduced or diminishes, and then after that of course it will not be there. So, with this we will stop over here. In the next lecture we will be discussing about basically various patterns what will be taking place from a nozzle, particularly under over expanded condition and under expanded condition. Thank you very much.